Whee! In this episode of the podcast, we're going to be looking at ramp problems. They can be unique because in ramp problems, up isn't really up anymore. Just another way physics rocks your world. I got two examples to show you. In the first example, we want to just concentrate on drawing the free body diagram because that's where the differences in ramp problems are going to show up anyway. Now, when we draw a free body diagram for a ramp problem, what we do is we actually take the axis and tilt it. We put the x-axis along with the ramp, and we take the y-axis and then put it at 90 degrees. What this is going to do is when we draw our free body diagram off to the side, it's going to put more of our vectors on the axes, and that makes them easier to do math with. What we're literally doing is we're taking a situation like this, where up is up and left and right are left and right, and we're taking the axes and we're actually rotating it. Now this rotational effect is going to come back to be important when we look at the weight vector, and we'll bring this diagram back then. But literally what we're doing is we're taking a standard set of axes that go up and down, left and right, and instead kind of turning our head so that left and right go along the ramp. The strategy is to always locate the forces on the ramp, and then what we'll do is we can then draw the vectors in the free body diagram. In the first situation, we've got a person on a ramp pulling a box up the ramp with a rope. In this example, we'll neglect friction. We'll have friction in our next example, so let's not complicate with frictions here. So we're pulling a box up a ramp, up a frictionless ramp with a rope. Well, the first vector to always make sure you worry about is the weight vector. Now, the strategy for locating the weight vector is to always locate it in the picture first, then try to put it in the free body diagram. You see, I've drawn my axes along the ramp, focused on the object itself, the box. Now, something you got to know about weight. It always goes straight down. Gravity pulls us straight down towards the center of the earth, so I'm going to take a vector and I'm going to draw it straight down here, and I'm going to label it mg. Now what we see here is that the vector is to the left of the y-axis in this case. Now depending on which way your ramp points, your weight vector could either be in the third or the fourth quadrant. But what we can see here by literally drawing the picture, drawing the vectors in the picture, is that the weight vector is to the left of the y-axis. So here I'll come in the regular free body diagram and draw it to the left of the y-axis. Now I'm going to mark an angle right here.
Colonel Lewis and Sergeant Major Shaw, please call the front office. Colonel Lewis and Sergeant Major Shaw, please call the front office.
I'm going to mark an angle right here, and that's going to be the angle that the weight vector makes with the y-axis. Now if we go back to this picture right here, the question is, what is that angle? Well, if we grab a marker, hey everybody, the question is, what angle does the weight vector make with the y-axis? Well, if we return to this diagram right here, we can see that if I raise the axes up, as we do, you can see the exact amount that I have to raise the axes up is the angle of the ramp. Now watch what happens if I draw a weight vector straight down in here. There's no angle right now with the y-axis if down is down. But watch what happens to the y-axis. Can you see that there's an angle opened up right here? And that's going to be the same angle as the ramp angle. So following that procedure, we can come back to our free body diagram, noting that weight points straight down in the picture, is found to the left of the y-axis. And so in our free body diagram that we're actually going to use to solve the problem, this ramp angle of 40 degrees is the weight angle with the y-axis. That's a rule that works every time. The weight vector angle will be the ramp angle, and it's always measured with respect to the y-axis. If we want to complete our free body diagram, all we have to do then is add the tension, and we can see in the picture tension goes up the ramp, so that would be to the right on our upright axis. And normal force comes straight out of the surface, so that's going to place it right along our y-axis. So remember that we were neglecting friction. So this is a complete free body diagram for this situation. We've got normal force, tension, and weight. Now sometimes you might want to know what are the components of the weight going the particular directions. So the part of the weight that pulls the box down the ramp is going to be the horizontal component, because remember, the horizontal direction goes up and down the ramp. So the horizontal component is going to be opposite of our angle, so that would be mg sine 40. And if we want to, if we did have friction, we need to know the normal force, and so we can see that that's going to be adjacent. So we can say that in an equilibrium situation here, that the normal force would be equivalent to and we're allowed to say that because we can clearly see that the normal force and the component of the weight are opposing each other, and there's no motion along this y-axis, and so they have to be equivalent to each other.